Okay, so I'm going to have you flip to the front side of that worksheet. I think the first triangle has two sides of 4, if I'm correct. I know it's a little bit hard to see on the screen, but I'll kind of just talk about, I think I went around to most groups and tried to find any errors and talk about those. For the hypotenuse on that first triangle, I mean, basically was the square root of 32, which you can simplify that radical. It's 4 square root 2. But since in the directions I said you could round to the nearest hundredth, I used 5.66. So then I go over and I do my sine, cosine, and tangent. Sine is opposite over hypotenuse, 4 over 5.66. Cosine is the same, 4 over 5.66. And then tangent is 4 over 4, which is 1. And I had talked to some groups about, in this particular case, we're not taking the sine, cosine, or tangent of theta. We don't even know what theta is, although some of you may have figured it out. So when we do trig ratios, like with the SOHCAHTOA, opposite, hypotenuse, and adjacent, the ratio is that fraction that you created. So you're literally just typing into your calculator 4 divided by 5.66, which both of those came out to be about 0.71. And then in the second triangle, I found my missing side to be 6.01 because of my rounding choices. The exact value is actually just 6. It really doesn't matter which one you use in your ratios. What you should notice is sine is 0.71, cosine is 0.71, and tangent is 1. We're very close to those things. Depending on your rounding, it might be a little bit off. And then in the last triangle, the missing side was 2. Okay, so this one was 6.01, and the missing side is 2. Okay, so you repeat the same process. O over H, A over H, O over A, plug it into the calculator and see what you get. Well, I mean, this is pretty obvious. When it asks you to comment on the work above, what was probably the first thing you said? They're the same, right? What's the same? Sine, no sins, sines, cosines, and tangents. Okay, so the sine of theta, the cosine of theta, and the tangent of theta were the same for all triangles. But were all triangles exactly the same? No. Did anybody use any of their geometry words to describe these triangles? Sorry, what? These are similar triangles. So that's another thing that maybe you notice. The triangles are similar. We kind of mentioned that maybe yesterday. Triangles are similar. And similar triangles means they're not exactly the same size and shape. That would be congruent. Similar means they're the same shape, but they're different sizes. So like you can see that in that first one, it had the 2 legs were 4. And then in the second one, that would be like a larger triangle because the 2 legs are 6. And then the last one, the 2 legs are 2. That would be a small triangle. Does anybody know what that theta is? Did groups talk about that? You actually know what theta is in this problem, even though I didn't tell you?
Is it the angle?
Yes. Do you know the measure of that angle?
Oh, yeah.
And on the front side. Alex? Okay, how did you guys reason that theta would have to be 45 degrees? Well, why did you divide by 2?
Because 90 plus 90 is 180, and there's 2 other angles with the same length, so they can't be different anyway.
Okay, so you might notice when you look back at all 3 triangles, each of these triangles have 2 sides that are essentially the same. You know, I had this one that was 6 and 6.01, but that's because of rounding. So if those two sides are the same, someone I think said it in one of our things, and there are two equal angles, right? And there are these acute angles. This angle is equal to this angle, vice versa. And so, yeah, we can just split up that 90 degrees, right? So then, if theta is 45, you might be thinking about this is one of my special right triangles. 45, 45, 90. So that's what's going to be in our notes here in just a little bit is you know something about 45, 45, 90 triangles and the length of all the sides around that triangle. Okay? So we're going to see that. But another thing that you're going to be thinking about here is that no matter what size your 45, 45, 90 triangle is, they have the same ratio, sine, cosine, and tangent. It's always the same. Okay, real quickly, we'll take less time on the back because we kind of already figured everything out. On the back side, if you want to check the answers that you have so far, the first missing side is 3.46. This missing side is 6. And in the last one, the missing side is 3.5. And then if you want to just check the first box, the sine of theta when you divide is like 0.87. If you have like 0.86, it could just be a rounding thing. Cosine is 0.5 or 1/2, and tangent is 1.73. And then if you do the sine, cosine, and tangent for the other triangles, same results, right? Sine theta, cosine theta, and tangent theta are all the same. The triangles are similar, that means. You might notice on each triangle, like you have two legs that make the right angle, and then you have the hypotenuse. The short leg and the hypotenuse are always half or double of each other, 3.5 and 7. Okay. Does anybody know which special triangle this is? This is our 30, 60, 90 triangle. That one maybe, like, it's not as easy if you don't, like, if you're not thinking about special right triangles. You could use this SOHCAHTOA stuff if you know about the inverse trig ratios. You could do, like, the inverse of 1/2. And whether you'd be doing inverse sine or inverse cosine, it will depend on which theta you're looking at. One thing to notice is that my theta, I had to be very strategic on this side. I always put the theta with the adjacent side as the short leg and the hypotenuse. So I have that the same in every triangle. That means that this theta was, we were really doing sine, cosine, and tangent of 60. Okay. If I had another sheet, I could pick the other angle and then we would get different answers. These two would just be flopped, but this answer would be different. Okay, so what the heck, who cares, right? This is where you're going to go to your notebooks. Okay. We're going to take a short set of notes, notes 9.1. We've got about 10 minutes remaining. Okay. May or may not take that much time. We're going to just put in our notes what we know about special right triangles. And remember, all of this stuff is stuff you actually know from geometry. It's been a while, so it was a little rough going at first for some groups, right? What the heck am I supposed to be doing? But we all really do know this. So I'm going to draw my two special right triangles. Get a 45, 45, 90 in there. 30, 60. Okay, so you should have some experience in geometry where if you saw one of the special right triangles, 30, 60, 90, or 45, 45, 90, you knew something about all three sides. That's the stuff we were like sort of seeing in the fact that they were similar. Some ratio of side lengths. Okay. And there's really two ways that geometry teachers will most commonly write these ratios. The way that I'll be using in Algebra 2 is this. So the hypotenuse, of course, is longer than the two legs of the right isosceles triangle. So the two legs are the same because the angles are the same. We're going to say that each of those are 1. They're like the base side. Like this is the measurement. Now, it of course doesn't always equal 1, right? Sometimes it's 4 and 4, 6 and 6 like we saw in our triangles. But if you do Pythagorean theorem real fast with this, these are the legs, so they're your a squared plus b squared. 1 squared plus 1 squared is 2. And then you have c squared equals 2, square root both sides. The hypotenuse is the square root of 2 times the length of the leg, right? So that's like the ratio, 1 to 1 to square root 2. Okay. The other way you might see a geometry teacher write that is they might say these are x's. Have you ever seen that? Okay, that's super helpful, and I actually do it in my examples. That could be super helpful if you're trying to it's clear that your leg is not actually measuring 1. So then you can try to find the other sides based on what that leg or hypotenuse actually is. So that's helpful to use. But later on in the chapter 9 when we get going, I'm going to drop all these x's and just use the coefficients, 1, 1, and square root 2. Because if those were your side lengths and you were doing opposite over hypotenuse, for let's say this angle right here, that would be x over x square root 2, and the x's will cancel out every time if all three sides have x. So we really don't need the x when we start doing the trig. Okay. On the other side, or on the other triangle, 30, 60, 90, make sure that you're labeling this one correctly. So I always start with my smallest angle, because opposite the smallest angle should be the smallest side, and we're going to call the smallest side 1. Again, that's going to be our base side. So if I know what that small leg is, short leg, then I know all the other sides of the triangle. Okay. The long leg, so the leg across from 60, is labeled square root 3. And then again, we could technically do a Pythagorean theorem here with this right triangle. 1 squared plus square root 3 squared, that's 1 plus 3. So c squared is 4, square root both sides, the hypotenuse is 2. And then likewise, you could label those x square root 3, 2x, or x. Okay. I am okay either way, so it really depends on how your geometry teacher did it that you might feel most comfortable. I'm okay either way, but I will eventually drop all those x's. Okay, so just really quickly, some example. Suppose I do a 30, 60, 90, and they can be oriented all sorts of ways. I do a 30, 60, 90. And I label the hypotenuse as 10. Let me call x and y for the other sides. Can you find the other sides? Yeah. Well, by ratio, remember, if you're thinking about it this is 1, square root 3, and 2. Okay, this is where your geometry teachers might have put x's in there. So that 2 times the short leg was really 10, therefore the short leg is 5. X equals 5. So this is saying 2x equals 10, x equals 5, so that goes there. And then for y, we would just take that short leg and multiply it by square root 3. So 5 square root 3. And I don't even have to do SOHCAHTOA or Pythagorean theorem. Okay. Let me see if I can get one more in. Yeah, I can get one more in. Another example. A harder one. How about? What if I draw you a 45, 45, 90 and the hypotenuse is 8? Okay, and then we want to find the legs. Well, what do we know to be true about the legs of a 45, 45, 90? They're congruent, so it really doesn't matter which one you find. Find one of them and then you know the other one, right? If I went around and labeled, ratio of sides, these are both going to be like my base unit. And then this one is the one that's the square root of 2 times that side. So like if I call that x square root 2, okay, and I'm thinking about the fact that that's like saying that short, or the leg times the square root of 2 is 8, how would I solve for x? Divide by square root 2, so x equals 8 divided by the square root of 2, and then I would rationalize. So times square root 2 times square root 2, that's 8 square root 2 over 2, which is 4 square root 2. So then this side is 4 square root 2, and this side is 4 square root 2. Which should make sense, because if that side was 4 square root 2, and then I multiply it by a square root of 2 to get the hypotenuse, square root 2 times square root 2 is 2, and 4 times 2 is 8. But that gets a little bit tricky, like you might have to rationalize the denominator. Now, you don't have any homework tonight, okay? You will eventually see some special right triangles somewhere in Chapter 9 homework, so if you know about them, you need to pull that information up from geometry and be able to use it. That would be my expectation. It's 12:42, so you're dismissed. Thank you for your patience. Have a lovely weekend.